All right, let's dive in. Today we're talking about one of the true unsung heroes of digital math, the 16-bit ripple carry adder. It's this really foundational circuit that lets computers do something as simple as add two numbers. And really, if you want to get how digital logic works, you've got to understand this. I mean, have you ever really thought about it? How does a machine that only understands ones and zeros actually do math? For us, adding two numbers is second nature, but for a computer, it's this whole cascade of logical steps. So what's really going on under the hood? Well, the secret isn't some huge, super complex chip that does it all at once. Nope. It's actually way more elegant. It's all about taking one tiny, simple piece of logic and then just repeating it, linking it together in a really clever chain. To get how a 16-bit adder works, we first have to look at the little engine that adds just one bit. And that little engine has a name, the full adder. Seriously, think of it like a single gear in a giant clock. Once you understand how this one little piece works, the entire machine just clicks into place. It all starts to make sense. So what is it exactly? A full adder is a digital circuit that has one very specific job. It takes three individual bits, adds them up, and gives you the result. That's it. Its power is in its simplicity. Okay, let's break down what goes in and what comes out. We've got our two main bits to add, A and B. But look at that third input, the carry-in. This is the secret ingredient. It's the bit that gets carried over from the previous addition. And the outputs, they're just as logical. You get a sum bit, which is your main answer, and a carry out bit, which gets passed on to the next adder in the line. The logic for calculating the sum is just beautiful. It's an XOR or exclusive OR operation on all three of those input bits. Basically, the circuit is just asking, is there an odd number of ones here? If the answer is yes, the sum is 1. If it's no, the sum is 0. Simple as that. Now, the carryout logic is just as important. This equation is all about figuring out if the sum is too big to fit in a single bit. It's asking a different question. Are at least two of the input bits a 1? If the answer is yes, well then we've got to generate a carry and pass it down the line. So, we've got our single bit adder down. But how do we get from adding one bit to adding two full 16-bit numbers? Well, the answer is just so cool and elegant. We just chain them all together. And this is how it works. You start on the far right with the least significant bits, A0 and B0. The first full adder does its thing, spitting out a sum and maybe a carry. That carry then ripples over and becomes the input for the next full adder, the one handling A1 and B1. It's like a line of dominoes. This just keeps happening one after another, all the way down the 16 stages until we finally get our complete answer. Now, this design is brilliantly simple, right? Easy to understand. But, like with everything in engineering, there's always a trade-off. And it turns out its greatest strength, that simple chain design, is also its biggest weakness. So on one hand, yeah, it's a dream to put into practice. The design is super straightforward, it doesn't need a ton of fancy hardware, and it's efficient with space. But the flip side is that it's slow. That whole ripple effect we just admired, it takes time. And that time is called carry propagation delay. And this quote just hits the nail on the head. The name ripple carry adder isn't just some catchy phrase. It literally tells you how the circuit works. And at the same time, it points right to its biggest performance bottleneck. Every single stage has to wait for the one before it to finish its job. So here's the bottom line. The total time it takes to get a final correct answer is the delay of just one adder multiplied by 16. Think about the worst case scenario. A carry generated at the very first stage has to travel or ripple all the way through the other 15 stages. In the world of modern computing, where things happen in nanoseconds, that is an absolute eternity. So how do we actually build this thing today? Well, engineers aren't sitting there soldering 16 little chips together. Instead, they describe the circuit using something called a hardware description language. And one of the most common ones is Verilog. And this is what that blueprint looks like. This Verilog code defines our whole 16-bit adder. You can see the inputs, A and B, are set up as 16-bit arrays, but the real magic is inside, where the code automatically creates those 16 full adders in a loop. It then wires them all up, taking the carry out from one and plugging it right into the carry in of the next one. It perfectly creates that ripple effect in code. So if we boil it all down, the 16-bit ripple carry adder is this fantastic, foundational piece of digital design. It's simple, it's elegant,
but its performance is fundamentally capped by the time it takes for that carry signal to ripple from one end of the chain all the way to the other.
And, that leaves us with a really interesting question. If this beautiful, simple design is the slow way to do it, what on earth does a fast one look like? How do you get around that ripple delay? Well, that's a whole other story. Thanks for joining me on this one.